tensor is H.
Sorry.
There should be a asymptotically flat initial data of the Einstein equation. And we also require that the matter fields, if we have the matters, and should satisfy something called the dominant energy condition. And then we can get following result. The first is that the ADM energy should be non-negative. And second one is a rejected result. It means that if the ADM energy equals to 0, and implies that the initial data should be the Euclidean space and the space-time should be Minkowski. And that's a standard positive mass theorem. Okay, and this theorem from the point of the physical, this theorem is quite natural, because that if we have no such kind of positivities, and then the gravitational system should not be system. But abstract proof, mathematical proof, is far from easy, and it's well known that the first proof is given by Professor Xiaoning and Professor Yao, and in 1979, and they also developed some many very useful mathematical technicals, and just 2 years later, Edward Witten also given another proof for the positive mass theorem, and they use another way to study the direct operator on the Riemannian manifold, and also give another proof. So the two methods is of course it's very important, and both of them are based on the partial differential equation techniques on the Riemannian manifold, and do not involved with the Lorentz geometry of the spacetime. And it's well known that for general relativities, and it's a theory on the Riemannian manifold, on the Lorentz manifold. So we want to ask a question, is that whether we can understand the positive mass theorem in the way of the Lorentz geometries. And the other motivation for this one is that, can we find a more physical ways, or means that for physicists, maybe they don't understand much more technicals about the partial differential equations, and sometimes they want to ask that how can we find some more physical way to prove or understand the positive mass theory? And that is the question. That's also the motivation of our works. So if we want to understand the positive mass theorem in a more physical ways, that means that we want to relate the positive mass theorem with some more practical physical process or physical phenomena. So the one is that we want to consider the binding of the light. It's well known that the binding of light is the first theoretical predictions of general relativity, and which has been confirmed by the observations in 1990. So this phenomenon is also very close related with something called the gravitational lensing, which is now is a very powerful method to study the cosmologies. So we can just consider the binding of light in the very simple case. That means in the Schwarz case, and we can show it's just in these pictures. That means we have light go inside from the right-hand side, and then if we have for example, a sun here, and then the gravity of the sun will bend the light, and the rate will go in this way. So that means, and the angle beta is just the binding angle of the light. Okay. Then in the Schwarz case, we can also calculate the concrete value of the binding angles in the very precise ways. First, if the light is just in the asymptotic flat regions, and we can use the post-Newtonian approximation, and then get that the binding angle is just proportional to the mass, to the total oh, sorry, my computer has some problems. To the total mass of the spacetimes, and also in the Schwarz case, and if we just consider, we want to consider the general case, that means the null geodesics are not only belong to the asymptotic region. You can also do the calculations and get the exact results, but one can just show that the bending angle is just a monotonic function of the total mass. That means you can take the derivative respect to the m of the function, and then we'll find that derivative will be always positive. And for the Minkowski, you will know that the bounding angle will be 0. So you know that the monotonic function, the beta should be the monotonic function of m. That means only for the Schwarz case. That's a very simple observations. So we can see that the bending of light is related with the positivity of the positivity of the total mass. That means that if the total mass is positive, and then you will bind it in this ways. And for example, if only for the Schwarz case, that if the total mass should be the negative, and then the bending of light should be going the other ways. Okay, just like this. Then in the general case, that how to describe, that means if we go outside the Schwarz case and consider the general case, and this should be described by the focusing theory, that the general form of the bending light. It's just an analog of the contacted point theorem for the remaining geometries. And here we only show the results get by Border in 1987. It means that if gamma is a complete, a fine parameterized causal geodesics, or means the time-like or null geodesics with the tangent vectors of the t, suppose that if the energy momentum tensor or the rich tensor is not negative too much, that means you can do the Usually we just require that the components of the rich tensor should be positive, but here we can allow that it have a small negative part, but total integral along the null geodesics should not be negative too much. And then we also have this one, something called the generic conditions for the remaining tensor. And then you will see that along this gamma, there at least have a pair of contacted points. That means that you start from one point, and then to consider another null geodesics very close to the gamma, and for finite time, and the two geodesics will come together. That is the focusing theory. Okay. So a simple observation of the Schwarzschild case shows that the bending of light is related with the positivity of the alien mass. So could we establish such a relations in the general case and the proof, and to use this way to another to give a proof of the positive mass theory? And this idea, in fact, that this idea is not come from me, but come from the Professor Roger Penrose. You know that in a very short essays written by Roger Penrose in 1980, he just gave these observations and then gave the conjectures. He said that crossing the result, that he conjectured that such of behavior or such kind of phenomena will appear in a very general case for the symptotic effect space-time with a positive mass. I think that this idea of the Penrose idea is not known for too many people. That maybe one reason is that during that years in 1980s, that the positive mass have a very nice proof by Professor Yao. So maybe not too much people just notice the Penrose idea. But Penrose also makes some attribute to realize his idea. In another short essays written by Penrose in 1990, in this journal, the Twister newsletters, and he re-expressed his idea in a much clearer ways. And also in another unpublished paper by Penrose and his students, they try to realize his idea in some precise ways. But unfortunately, they haven't do this. They haven't do these things in a very precise ways. The main difficulties which Penrose et al. Made was that what we want to do is to get a very precise control on time-like or null geodesics in a very general case, in a general asymptotic flat space-time. So you know this is a very difficult thing. So maybe that's the reason why it's a paper in 1993. It's not very successful. Okay, but something is maybe a little surprising is that just 1 year later, one of his students, that's E. Uga, he has achieved Penrose's idea just in the asymptotic ADS case. Usually, maybe the people think that the things on the asymptotic ADS case will be a little difficult than the asymptotic flat spacetime. But just for this problem, the things is just in the inverse way. That means the asymptotic ADS case is more simple. Yeah, here is the result just guided by Uga, and his result can be explained in these pictures. That means here is a asymptotic, it's a conformal computation of the asymptotic ADS spacetime, and the cylinder here is a conformal infinities. So it has a cylinder structures, and the generator is just a time-like directions. Okay, and then what Uga then is that let's consider the 2 points on the section of the conformal infinities. That means on the 2 spheres here. And here is a point P, and the other is a point at anti-point positions. So you consider these 2 generators. We consider 2 null geodesics. The first one is start from the P and always go inside the conformal boundary. That means you just consider the null geodesics inside the conformal boundaries. And because of you can write down the metric just inside the conformal boundary precisely, and you can do direct calculation and write down the solutions of this null geodesics. And you can show that this null geodesics from the P and to the, let's just call them Q, to this point, and along this part, there are no contact point just inside in the section of the null geodesics. Then you can consider another case of null geodesics also start from the P, but they will go inside the spacetime. That means not belong to the conformal boundary, but go inside the spacetime. And then also arrive at the same generator of the conformal boundaries. That means intersect with conformal boundary as the Q prime. So there is a distance in the t direction, that means a delta t, and then you can just based on some causality analysis, and you can show that such kind of the delta t should always be positive. That means be bigger than the zeros. And then you can, because the smoothness of the conformal near the conformal infinities, and you can just write down exactly the geodesic just inside the space-time precisely, and then you can do really get the result how to express the difference of the t, and just by these ways. Then, in other words, is that in the asymptotic ADS spacetimes, you can have an analog of the ADM mass expressions, something just like expressed in this way. Here is the wave tensors, and the E is the electronic part of the wave tensor. And you can find this one is just something analog to the ADM mass of the symptotic spacetime. It is the energy of the symptotic ADM spacetime. You can find this result in some works, for example, by Abe Eshtek and some other peoples. Then with the positivity of the delta t, and you can prove that the mu is always should be the positive, at least in the time mean levels. That means you can see that at each sections of the conformal infinities, you can get the value of the mu, but not each one, maybe not each one is positive, but the time average of the mu at from the section start from the p, sorry, and then until the section just goes through from the q, the time average in this section should be positive. That's the result get by Uga. It means that if we just consider stationary case, and then we can get the positivity of the energy in the symptotic ADS case. So that is the first case that we can really achieve Penrose idea for the positive mass. And in 2000, Galloway get a very interesting result. He calls them the null splitting theorem. That is an analog things. All you can see is a Lorentz version for the splitting theorem of the remaining geometries. And based on Galloway's result, he can get a very important corollary, just like this. He says that if M is a asymptotically simple vacuum spacetime, a asymptotically simple spacetime means that first, the spacetime is asymptotic flat. Secondly, that every null geodesics in this spacetime is complete. So something just calls it asymptotic simple, which means that you have the spacetime but contains no black holes. If such kind of spacetime contains a null line means that you have a complete null geodesics but contains no contact points. If you have such kind of things, then the M must be Minkowski space. That is a very important corollary just based on Galloway's null splitting theorems. And based on this result, Professor Crucial and Galloway also give a result about the positive mass theorem. That means they just call them poor man's positive mass theorem. They say that if the spacetime is a uniformly asymptotic to Schwarzschild spacetime, that means and the vacuum simple satisfies the vacuum and simple conditions, and such kind of spacetime cannot have a negative mass, and the zero mass implies the Minkowski. And the main idea of Crucial and Galloway's proof is just that for based on the non-positive mass assumptions, and use the causality analysis technicals, they can construct a null line in such kind of spacetimes. And then, based on the result get by Galloway, they will show that such kind of spacetime is only Minkowski, and then to tell us that the negative mass is impossible, and to get the zero mass is and the following to get the positivity of the spacetime, the mass of the spacetime. Now, before to introduce our results, we just try to remember some basic knowledge about the causal structure of the spacetime. I mean, first we should say what means the causal curve. So based on if we have some Lorentz metric, now we use the signature is plus minus minus minus, and that is a convenient way. For any tangent vectors, if the Lorentz normal of the vector is bigger than 0, we will call them time-like. Equals 0 is null, and smaller than 0 is space-like. And this is a little different from the common textbook because we use plus minus 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 signatures. Okay, and then if curve is called a null and time-like and space-like if the tangent vector should be the null, time-like, or the space-like. And then we will call the time-like or null curvature is called the causal curvatures. That means that if a 2-point connected by the time-like curve or the null curves, and the 2-point can have some physical relations. That is just based on the very famous assumption of the relativity. That means any signals or energy cannot transport faster than the speed of light. Okay. And we also need to define some chronological set or causal set, something like this. It's a +1 means that if a P belongs to if the Q belongs to the +1 I plus of P, it means that from P to Q, they have a future directed time-like curves. That means the 2 points have been connected by a time-like curves. If a Q belongs to the future causal set of P, it means that from P to Q, there is a null or time-like. That means you can use the time-like curve or a null curve connected from the P to Q. And the I minus and the J minus is defined just in this way. So it means you can go to the plus means go future, and the minus means go past. Okay. And then there is a definition for the asymptotic simple spacetime. That means spacetime is asymptotic flat and not that is complete. And we have introduced before. It means that such kind of spacetime which contains no black holes. Okay. Another thing is that we want to consider the conformal infinity of the spacetime. That means this one is also introduced first by the Penrose. And he says that if the M tilde and G tilde is a Lorentz manifold and satisfies Einstein equations, and we call the spacetime is to be asymptotic flat spacetime, then if that we can find another, when we call them unphysical spacetime M and G, such kind of the two manifold is related by some mappings, and then the M is a little bigger than M tilde, and the boundary of the M is just compiled by the 3 part, and this is this one. Don't hear me?
Yes.
Okay.
Yeah. Yes.
And the I naught, okay, the I naught we call them special infinity, and the I plus means the future non-infinity, and the I minus is the past non-infinity. And then the relations between the I plus and the I minus with the I naught of the causal set of I naught, and the I minus should be the boundary of the past causal set of the I naught, something like that. And then you can also relate the two metrics by the conformal transformations. That means you have a conformal factor here, which is only take the 0 value on the boundary, and then the negative is the inner of the unphysical formal relations, something like that. So there's another very important thing, so we'll call them Penrose property. So it means that if a asymptotic simple spacetime which satisfies the Penrose property, it means that for any point P belong to the past future infinities, and then the I plus of the P for any P belongs to the past future infinity. If such kind of property holds, we call such spacetime satisfies the Penrose properties. Okay. So we can see some simple examples. That means the conformal compactifications of the Minkowski spacetime. So you can introduce the two null coordinates, something like that, and then define the new chord, the new chord pi just by these relations, and then to use the conformal condense and introduce to get some metrics. We call yeah, here is the Minkowski metric. We just note some as a eta tilde, just following the habits here. And then you can define the conformal compactification metric of the Minkowski spacetime is the eta, and then it's the eta tilde times the conformal factors. You can write down this metric in the coordinate t, chi, and theta phi, and write down the conformal factor here. If the shadow part corresponds to the Minkowski spacetime, and then the dashed line is the future infinity of the Minkowski, and this part of the dashed line is a past future infinity, past non-infinity for the Minkowski spacetime. And we also introduced some weakly simple spacetime. We need to find it's because that in Galloway's work, and they need the spacetime should be simple. That means the spacetime contains no black holes. We just want to generalize this part or to relate this one. So we need to introduce the definition of the weakly simple spacetime, and it means that the spacetime is not always the order that it's not always the order that it complete. We only require that it's a asymptotically flat spacetime, and in the neighborhood of the special infinities, there is a neighborhood of the special infinities. It satisfies something called the global hyperbolic properties, and should know what it means. It's the global hyperbolic ones. But should I explain it? Should I explain what means global hyperbolics? Or maybe should I explain what means the global hyperbolic of the neighborhood? Or maybe I think everyone knows that. Okay. And then another thing is that we need the any geodesics inside the neighborhood should be complete. It means that, for example, if we have a geodesics inside the neighborhood of I0, it will only have the endpoint, because in my slide it shows that my Wi-Fi has some problems. So I'm not sure that you can hear me. Is it okay?
Yes, but
okay. Okay. So it means that if a geodesics just inside the neighborhood of the I0, it can endpoint on the future or past non-infinities. The other is that they have endpoint on the boundary of the neighborhood. It means that another that cannot be broken inside the neighborhood. So we call them a weakly simple spacetime. I think that it's quite natural, because that based on the definitions that the income of singularities. So we say that if we are in the symptotic regions, there are no singularities in the neighborhood. So I think that is quite natural requirement for that. That means this one is okay, but this one is impossible. Okay. Following, we also need to introduce some very useful facts. But in fact, that's both all of them are theorems that about the causal structure of spacetimes, and you can find this result in Hawking's very famous book, The Large-Scale Structure of Spacetime, in the chapter 6. The first one, the first one is that if P and Q is a pair of contact points on a geodesics, then there will exist a time-like curve between the P and Q. It means that if the null geodesics contains a pair of counted points, and then you can use the variation method just to perturb the null geodesics between P and Q, and then you will get the time-like curves to connect it to points. That's the first fact. The second one, the second one is that the I means I plus or I minus is open side, and then the I plus J equals I, and this one is only a simple way to express it. The meaning of this equation is only tell us that if you have a 3-point A and B and C connected by 2 parts of the causal curves, maybe one part is time-like, the other part is time-like or null. Then you can always perturb this curve, and then to get another curve is totally time-like. So it means I plus J equals I. It means that from the point A to point C, you can get another curve connected to 2 points, and this curve is just time-like, totally time-like. That means the I plus J equals I. And the factor 3 is that PQ is 2 points which connected by a null curve gamma, and then only the two cases is possible. One is that the gamma is a smooth null geodesics. The other possible thing is that there will exist another curve is time-like which connect the P and Q. It means that for the 2 points, if they connected by a smooth null geodesics, that's okay. If they are not connected by a smooth null geodesics, but also connected by some causal curves, you can always find some time-like curves connected to P and Q. And this is a very important properties we will need in following. The factor 4 is that suppose that C is a closed set, and any Q belongs to the boundary of the coordinate set of C. That means the I plus the boundary of the I plus of the C. Then they will, for any points Q belongs to the boundary of this one, then there will be exist a path directed null geodesics gamma start from the Q and go back to the C set. And then, the null geodesics belong to the null geodesics will belong to the boundary of the I plus of the C and the Q. There are also 2 possible conditions. The first one is that the gamma is path inextendable. That means that this null geodesics go back and will meet some holes and will not go to the C. The other one is that this null geodesics just go directly to the set C and has an endpoint in that. It's only 2 possible ways. And you can imagine it very simply in the Minkowski case. Let's consider some a light cone in the Minkowski space. It just starts from 1 point. So we just take the 1 point as the set of C is a closed set, and then to take another point on the light cone. From that from that point, you can go back along the generator of the light cone and then just arrive the start point of the light cone. That means the second one, we have an endpoint in the C. Otherwise, if you remove some points from the light cones, and then you will have some generator will be broken, and then you will find the first case. That means gamma is past inextendable and cannot arrive the C in that meanings. Okay, that is the factor 4. The factor 5 is also very useful. That means if a neighborhood is global hyperbolic, then for any PQ belongs to the O, so the intersect of these 2 sets should be first is compact all will be empty. That means they will not intersect. The intersect of these two sets can only be the two. Can only be one of the two cases. That means it be a compact set. Otherwise, it will be empty. Okay. Now, based on these things, we can state our main result. That we say that suppose that M and G is a weakly symptotic, empty, and simple spacetime. Yeah, here we only need the weakly symptotic simple spacetime. That means that in the spacetime, it not means that every node that is complete. It's only in the neighborhood of the special infinity. Inside the neighborhood, the node that will be complete. And in the space, and such spacetime satisfies all the conditions of Border's focusing theorem. The Border focusing theorem is very important for our proofs, so we need the conditions, all these theorems. If the physical metric G is stationary, now that is the disadvantage of our result. Now we can only consider the stationary case, and until now we don't know how to generalize our result to the more general case. With a mass M, then the mass cannot be negative. That is the result we can get. Which means for the stationary asymptotically empty and simple spacetime, the total mass should be non-negative. That's the result we can get now. Okay, here we talk about the sketch of the proofs. The first one is that why we need the stationary conditions. It only means that for the stationary empty spacetime near special infinity, we can have following asymptotic expressions for the metrics. And this result is got by Beck and Simon in 1980s, and also Damore and Schmidt in 1990s. Okay, and here the F, the 3F is only means the higher order terms. That means that it not means that in these terms only contains the 1 over R, 1 over R squared, and 1 over R triples. The higher order terms we just put in the function f and fi and fij. It means the higher order term is just this part. And here the m is just the total mass of the spacetime, or the ADM mass of the spacetime. So for the stationary spacetime, we can have the general expressions for the spacetime metric. Then we can introduce the intermediate metric H tilde and defined by this way. It's just a diagonal metric and contains the two functions A and B, and the functions are only the functions of the radius. And the definition of the A is here and definition B is here. And here G is not the gravitational constant. It's only some constant that we need to fix following. Okay, you can introduce such kind of intermediate metrics. And then we will introduce some note is that we call that if we have a two metric G1 and G2, if we call that G1 is smaller than G2, it means that for any tangent vectors, that the Lorentz norm of G2 is always bigger than the G1's Lorentz norm. Then we call them that G2 is bigger than G1. Okay. Then we can state the first causality comparison theorem. That means if the m is non-zero, that may be positive or may be negative, but it's non-zero. This m is just the m in the general expression for the matrix. Oh, sorry. Oh. Then we can always find a positive constant g bigger than 0. The g is just a constant in the function a. And you can also find another positive constant is the R0. And that if the radius is bigger than the R0 in the neighborhood of the special infinities, you can always have following controls. That means the metric H tilde introduced by us is always bigger than the G tilde. The G tilde is a physical metric here. And this one means that a G causality, what means the G causality is the causal vector just considered based on defined by the metric G tilde should always be the H causalities. It means that if a vector, a tangent vector, you measure based on the G tilde is causal. And because of these inequalities, you can always find if you consider the same vector just based on measure the same vector just based on the H tilde metric, is also a causal vector. Okay, that is great. Secondly, we also need, because we want to consider the problems in conformal ways, so we need to do the conformal compactification of the space-time. That means the space-time described by the G tilde here. And just like what we have done for the Schwarz spacetimes, and we can introduce some total coordinates R star just by these ways, and you can express it in a power extension ways, and then to introduce the something just like the Eidingen coordinates U and Y, something like this, and then to similar to introduce some coordinates capital T and chi, and then you can do this conformal transformation to introduce such kind of conformal factors, and then to do the conformal compactifications for the spacetime of the G tilde. That means the G equals the omega squared times G tilde, and you use the same conformal factors to conformal compactify the metric of the H tilde and define like this. So since the conformal transformation will not change the causal structures, so obviously you can know that in the conformal spacetime, you can always have such kind of relations that the H is bigger than the G. The H and G define just like this, which means that the G causal also implies H causal. Okay. Then we will back to consider the conformal compactification of the Minkowski. So this we have expressed before, and we have introduced before. That means the Minkowski spacetime and the conformal Minkowski spacetime and conformal factor you can express in this way. Then, secondly, we can get the second causality comparison theorems. And this one, I should emphasize that this one is a key point for our proofs. It means that in the neighborhood of the I naught, which is covered by the coordinate T chi we have constructed. For the conformal space, then if we assume that the total mass should be negative, here the total mass just the mass in the G tildes is a negative. Okay, you can show that the following inequalities. That means the G is smaller than the H and also smaller than the eta. And this relation only holds for the negative mass case. So we can show these relations. And this means that the G causal implies the H causal, and the H also implies the eta causal. That means the light cone defined by the eta or the conformal Minkowski is the biggest one. And the light cone defined by the H is smaller. And then the G is the smallest one. And this causality comparison theorem is a key step in our proof. The main idea is that to compare the causal structures of the physical spacetime always with the Minkowski spacetime. That's the key point. And let me remember you that in the original paper in the paper by Penrose in 1993, why they are not very successful is only because they want to get some precisely control about the behavior of the time-like geodesics or the null geodesics. But in this ways, we don't need to get such kind of, we can avoid such difficulties just by compare the causal structures defined by the physical spacetime and the Minkowski, and compare with the two causality structures, causal structures, and then to get to control the behavior of all the null curve or the causal curves. Okay, that is the key point that we can finish this proof and we can get our result. And this idea is partially motivated by a work by I guess maybe this one is a student of Penrose. It's named Cameron or Danaski. I'm not sure whether my pronunciation is right. And they published some paper in 2000. Okay. With these two kinds of causality comparison theorems, we can just to tell you how to get our final result. Here, we use a contradiction argument for the main theorems. The first one is that just based on direct calculations in Minkowski, you will know that for the Minkowski spacetime, the Penrose property is fail. That means that you can show the picture here. It means that here is a conformal compactification of the Minkowski spacetime. If you just choose any point in the past non-infinity, you call them P prime. And you can always find some Q prime in the future non-infinity. And for the spherical coordinate, it's just at the endpoint positions. And then you will find that in the right line, on the right line, all these points belong to the right part of this line, cannot be connected with the P prime just by some time-like curves. That means that the Penrose property is fail. Okay, this means that for the Minkowski case, the Penrose property is fail. Then, based on this, and remember the second causality comparison theorems, you will know directly that for the weakly simple stationary spacetime and with the negative total mass, the causality comparison theorem will imply that Penrose property is also false, right? Because that we have to know that for any curves, if it is the causal, if you measure, if a curve, you measure it based on the G matrix, it's a causal curve, which implies that if you measure the same curves just from the Minkowski matrix, it must be a causal curve. But in contrary, if a timeline, if a curve measured by the Minkowski should be space-like, and it cannot be the time-like if you measure it from the physical matrix, from the conformal matrix G. Okay, so you get that the Penrose property for the negative weakly simple stationary spacetime should be false. If you know that the Penrose property is false, and then you can see that, oh sorry, here is a typo. Here should be, you can always find that it should be exist, the P belongs to the past non-infinity. Yeah, just in the neighborhood of the special infinities. You can always find such kind of point, such that there is a Q belongs to the future non-infinity. And then the Q is not belong to the I plus of the P, which means that you can always, for the physical spacetimes, you can always find some Q, which also cannot be connected to the P just by some time-like curves. Okay, it's not belong to the I plus of the P. And the square plus is complete at least in the neighborhood of I naught. I mean, we require that at least in the neighborhood of the I naught, that I plus should be complete. So you can find that I plus intersect with the boundary of the P plus is not empty, because at least you have one point there, okay? And you can also control, you can also know there is a points Q hat is just on the boundary. And furthermore, because you have the causality comparison series, you can just know where, in some meanings that you can always know where is the boundary here, because it must be always outside the boundary, just in the Minkowski spacetime. But for the Minkowski spacetime, you can always do the calculation directly, so you know that such kind of things will be always exist. And the global hyperbolic and the simple property ensures that there exists a complete null geodesics from the P to Q. And this why it's just use these properties. I should remember you that we just use this fact. It means that the P is just the closed set C. And then because the Q hat is just the position of the Q, and then because the Q hat belong to the boundary of the I plus of the P, so you have a past directive null geodesics belong to the boundary, and then from the P of the Q. Why the first case is not possible is only because that in the neighborhood we have required the completeness of the null geodesics. So the first one is not, it's impossible. So the second one is the one it's possible. Okay, that is the reason why you can always find such kind of null geodesics from here. So if you have such kind of null geodesics, you will meet two cases. The first case is that this null geodesics belong to the conformal boundary completely. That means that if you see these pictures, it means that your Q hat is here. Okay, the first one is that you just go inside from the boundary, conformal boundary, and then through the I naught, and then to go to this null geodesics to the P prime here. You want from the boundary. I'm sorry, this picture's not. So the P prime is here, but the Q hat should be something like should be at such kind of positions. I mean, away, a little away from the Q prime, and then the null geodesics should be the generator just belong to this one, and then come here. So such kind of curves is not a smooth null geodesics, and then based on the factor, I mean based on the factor 3, if the null geodesics is not a smooth null geodesics, it must be another time-like curve from the gamma prime from P to Q. And this means that such kind of points, the Q hat should be belongs to the I plus of the P, but that is a contradiction. So that thing is impossible, which means that the null geodesics connect the Q hat and the P should not belong to the boundary, the conformal boundary of the spacetime. Then it will be go inside from the spacetimes. If it go inside the spacetimes, we will use the factor. We will use the factor 1. It means that first we have no such kind of null geodesics just on the boundary of the I plus of the P. So it means that from the 2 points of Q hat to the P, there are no null geodesics. There are no time-like curves connect these 2 points. That means that we have that means that the Q hat belong to the boundary of the I plus of the Q, because here we have no, the I is open side. If you belong to the boundaries, you cannot have the time-like connections between the Q hat and the P. But since the null geodesics just go inside from space-time, and then there are no inside inside the space-time, and the space-time will be satisfied the borders focusing theorems, and the geodesics is complete because the whole geodesics just belong to the neighborhood of the spectral infinities. Based on the focusing theorem of border, there must be at least a pair of contacted points. If you have contacted points on the null geodesics, between the two contacted points, you will find some time-like connections. Then you can also use the factor, maybe you can use the factor 2, it means I plus j equals I. So it means you can perturb this piecewise causal curves to get a totally time-like curves to connect the Q hat and the P. But this contradiction with the assumptions that the Q belongs to the boundary of the I plus of P. So let's get only the two possible cases always have the contradictions. So we have know that we cannot assume the M is smaller than 0. So which means that we get the positivity of the total mass of the stationary spacetimes. Okay. So let's summarize our result. First is we implement the idea of the Penrose to investigate the physical incoherence of negative mass of the spacetime. That means that if you have a negative total mass of the spacetime, it will be incoherent with the border focusing theorems. That is the original idea of Penrose. The secondly, that the spirit of the proof is rely on the properties of the spacetime in the neighborhood of the conformal infinities. That means we only need the properties in the neighborhood of the spectral infinity. Yeah, of course, only based on the causal structures of spacetime. So we don't need the whole spacetime should be simple. So our methods should be deal with some case can be used to deal with spacetime contains black holes. So it's a little general than crucial result. But the disadvantage of our method is that we can only get the positivity of the mass, but we cannot get the rejected result for the 0 mass, because that in our method we can if the mass equals 0, we get nothing. So it means that the rejected result for the 0 mass is still open. If compared with a crucial result, some local version of the not splitting result maybe is also needed. And we until now we don't know how to deal with this part. The four is that how to generate our result to the non-stationary case. I have explained that why we need the stationary condition is because in the stationary case, we can have a very general form of the metric, just we have shown at the beginning. So in the non-stationary case, we have no such kind of expressions. So it's one of the difficulties. But it means that we need some more detailed controls on the spacetime metric near the spectral infinity. But until now, we don't get that. Or finally, we also consider that maybe this method can be generalized to other kinds of gravity theories. For example, some modified gravity theorem, because the causal structure may be not modified very much. So maybe we can generalize this method to some other gravity theory. Okay, and thank you very much for your attention.
Thank Dr. Xiaoning Wu. Thanks for your good talk. Anyone has question or comments?
Perhaps I can jump in with a minor comment.
Mm-hmm.
Eric Woolgar here. Raphael Sorkin and I weren't actually students of Roger Penrose.
Mm-hmm.
I was a postdoc of Sorkin, who was a professor at the time.
Sorry.
It's okay. I'd be delighted to have been a student of Penrose, but I wasn't.
Okay. Okay.
Did you try in higher dimensions, by the way?
In higher dimension, I think maybe it's okay because that, for example, by Dr. Camelon, and they also consider the higher dimensional Penrose properties for the maybe Schwarz or more general case. I think that this method could be generalized to the higher dimensional case. But I think that, but for me, the most important things is that how to resolve this kind of disadvantage. That means how to get the geodesics result for the zero mass, and also to see how to remove the stationary requirements.
Sure, of course. Although I
higher dimension, I guess maybe it's right.
I suspect that the issue number 3 on your slide, the rigidity case, is going to be. I suspect the same problems will come up in higher dimensions, but it might completely invalidate the proof because the fall off for the mass term, the fall off will be like mass over r squared. And that's not strong enough to to deflect null geodesics near infinity. So I suspect it will look very much like the zero mass case in 4 dimensions, but I'd be interested in seeing.
Yeah. Frankly, I have to say that for the zero mass case until now, we haven't have some very clear ideas.
Well, thank you. A very nice talk.
Thanks.
May I make a comment?
Okay.
Greg Galloway here. The null splitting theorem does localize. You don't need null geodesic completeness of the entire space-time. If you look in the paper, and I don't know, you need some null geodesic completeness, but not of the entire space-time. And the null geodesic completeness that you need may be satisfied in your situation. I'm not absolutely certain, but you could check back with that old paper of mine.
Okay. You mean that for splitting theorems that you don't need the whole space-time should be simple. Only a part of them is okay.
Yes, that's correct. For the null splitting theorem, that's correct.
Okay, I think that
point is made somewhere in the paper.
Okay.
Exactly. Exactly the null.
I think that I should read your paper very carefully.
That's okay. It's okay.
I think that is a very useful, very powerful tools. Okay.
Thank you.
I remember the last time I meet you, you tell me that this theorem is your heart.
Really? I had fun with that. Thank you. Yes.
Yeah. Okay.
Hi. Thanks for your talk. I was just wondering, could you explain again why the curve that you constructed between the 2 points, why you know that doesn't just lie on the conformal boundary? I don't think I quite understood that bit.
I mean, it's that here.
And I should also,
sorry. I mean, it's that, okay. I mean, it's that, first of all, it's that for the Minkowski, you can do the direct
Yeah.
calculations, right? Then you will know that where is the boundary, at least for the Minkowski case. I mean, that at first you know that the antipole points, of course, cannot be cannot be connected by time-like curves because of the causal comparison result, right? Because in the Minkowski, the p prime cannot be connected to q primes, and you can also do the direct calculation for the Minkowski case. You will know where is the boundary. For example, maybe the boundary is here. Okay, and then for the metric G case, for the G metric, and you know that because you have the causal comparison theorem, so you know that the boundary, in this case, you don't know where exactly the boundary is, but it should be always outside the boundary of the Minkowski, right? Even more far away from the q prime.
So I think the
right?
thing
Because,
in Minkowski, I think that causal boundary is the conformal boundary. You can reach all the points except the antipodal ones.
Right.
So I'm not sure if you.
I mean the boundary. No. Maybe I haven't explained where. The boundary, I mean that it's just the boundary of the I plus of the P and intersect with, for example, the section of the future non-infinity where the P prime belongs to. That means that for Minkowski, you will know that the P point, the P prime cannot be connected with the Q prime because the P and the Q are just in the antipole positions.
Yeah.
Right? This way you can show just based on direct calculations, because that's in the Minkowski, everything you can calculate it. And then you can know that where is the boundary for the Minkowski case.
Sorry. Can you hear me, Dr. Xiaoning?
I think we've lost his sound, but Peter, I was also confused on that point.
Yeah.
So I'm glad you brought it up.
Yeah, I guess so I mean I'm Peter Cameron that's been referenced, and I should also point out I'm not old enough to have written a paper in 2000. But so yeah, I wasn't sure, because when I did that calculation in Minkowski, you can reach all the points except the antipodal one. So the boundary of the causal future of that point is the conformal boundary. So I don't know how you can conclude that. I mean, this is why you had to do these actual calculations to conclude that those curves didn't lie on infinity. I'm not sure you can just use that comparison argument. Sorry.
Yeah, I'm also a bit puzzled by that, I have to admit.
Yeah.
Did we completely lose the speaker? He seems to have disappeared now. Maybe he's going to rejoin.
Yes.
Maybe I can reach out to him.
I think he's gone. I don't think he's coming back.
Maybe he is reconnecting.
Hopefully.
Yeah.
I don't see him coming back.
Sorry.
By the way, Peter, I'm not sure if I remember. I think we had a little bit of correspondence about this a few years ago. Is that right, or am I inventing that?
Yeah, we did. Yeah, yeah.
Ah, okay.
Yeah.
Where are you now then?
So I'm still in Cambridge. I'm actually at UCLA for 3 months just now.
Okay.
I've actually started thinking about this again in the last couple of weeks. Piotr Khrushchev from the other positive energy proof that was mentioned here. He was here for the last couple of weeks, and he's given me some suggestions on things to think about. I was actually trying to use these same kind of comparison ideas, but removing, but not making kind of global assumptions about the space-time, just trying to do it on an initial data surface, and then using a Corvino-Shane kind of argument. I've been thinking about that the last couple of weeks, because it would be nice to kind of have it as a, conditions on an initial hypersurface rather than global, and see if I could use these comparison arguments. Yeah.
And we're not going to get the speaker back.
Hello, Peter. I think we met in Mittag.
Yes. I think that's where I came up with this this idea that I had.
Right.
Yeah.
Very nice.
Yeah.
And so you spoke with Piotr Khrushchev while he was in UCLA.
Yes. Yeah.
He had some questions about your work. I know he had mentioned.
Yeah. I'm hoping I managed to win him over. He was quite skeptical of it, but I think I managed to win him over.
Very good.
We'll see.
Very good. Anyway, I have to sign off. Thank you very much.
Oh, is this him coming back here?
Can you hear me?
Yes.
Okay. Yeah, I'm sorry because the Wi-Fi in my home maybe not very good. So I changed another computer. But unfortunately, in this computer, the camera is out of work. So let me to explain it. Okay. Suppose that here is the I naught, and then you can choose some point P here, and in the in the antipole point, there's a Q prime here, right? That means here is the theta equals 0 and the phi equals 0. And for this point, it's that the theta equals pi and the phi equals 2 pi. Okay, and in Minkowski, you can do the direct calculation and to show that this kind of these 2 points cannot be connected by the timeline curves in Minkowski, only in Minkowski. Okay, you can just do the direct calculations. Then you can also know that the boundary, we only consider the points on the sections, on the same sections with the Q prime, all these points in those 2 sections. And we will find that where is the boundary for the points, maybe here and here. And just inside the boundary, that means for this point, you can always find some timeline curves connected with a P just inside the space-time. And
sorry to jump in there. The calculation in Minkowski is that boundary is actually the point Q prime. That you can connect every point with a timeline curve except Q prime itself.
Okay.
There isn't a separation there.
Okay.
Yeah.
Okay. So for the but we know that that is the reason why we always need that the I'm is not equal to 0. I mean, for any finite points, that because we have the control is the G smaller and equal than H, but exactly smaller than the eta, right? So you can always have some boundary. So here, and then you will have points that
Don't think
for
so.
this
No,
point.
again, sorry to jump in again, that in negative mass, again, you can't, I'm pretty sure, I'm not sure I've actually done the calculation, I'm pretty sure that you can reach, again, the situation is you can't reach the, no, it is that you can't reach the antipodal points, but again, you can reach all the arbitrarily close ones. And what happens is as you get curves that get closer to the antipodal ones, those curves escape to infinity. And so if you try to take a limit of that, it would live on the conformal boundary, which is the thing you're trying to rule out. And I think that's why Eric and the collaborators back in the day had to get this actual precise estimate, and that these comparison arguments weren't working.
I'm sorry that I think that okay, let me think. You mean that even for the I, it's just smaller than at some finite distance from the zeros. You can always find some close to that.
Yeah. I mean, I'm pretty sure that's the calculation I did. Yeah, you can get as close as you want, because all it's telling you is that m less than 0 is kind of, it's harder to connect the points than it is in Schwarzschild. The positive mass is kind of deflecting you, the negative mass is deflecting you away. But you know that in Minkowski, sorry, in negative mass Schwarzschild, it's harder than in Minkowski because the mass deflects you away. And in Minkowski, you can get arbitrarily close to the antipodal points. So all that it tells you is that it's no better, but it happens to be no worse as well, I think, in the sense that you can still get as close as you want.
No, I mean, so, but you can just you can always choose this points is close to the I naught enough. I mean that.
Oh yes.
If this point is very far away from the I naught, I agree that what you say is right. But if you take the Q prime is close to the I naught enough, then you can always have.
No,
There's never an open set. There's never an open set of Scri plus that is outside the future of P. Every open set of Scri plus intersects the future of P, no matter what the sign of the mass. I'm sure of that.
Yeah.
Really?
Yeah. So when you try and construct this geodesic, it will live on the boundary. Yeah.
Okay, maybe I should reconsider this part. Okay, thank you.
Yeah. I mean, I'll maybe go away and check that calculation, but I'm
okay.
Yeah, it would be nice to be able to just do it with just comparison arguments rather than having a calculation. And yeah, I'm kind of wondering if that is possible. It's something I've been thinking about in the last couple of weeks. But
okay.
Yeah, it's just this fact that there isn't an open set, I think, makes it quite difficult.
Okay. Okay, thank you.
Anyone has other question? So even though we will end today's talk, and thank you for everyone to.
Okay, thank you.
Thank you everyone to. Okay, it's the end of.
Thank you.
Thank you.
Thanks.